operating the Airtable. This video introduces you to the Airtable, showing you how to use it safely and how to use it in laboratory experiments. Geared for faculty and teaching assistants, this video supplements the Department of Physics Lab Manual. However, students may also find the video useful to add to their classroom instruction and hands-on practice. This video is in two sections. In Section 1, we will show you how to use the Airtable and highlight the safety procedures you should follow. Section 2 shows you an experiment using the Airtable and lists additional laboratory experiments. Section 1, Introducing the Airtable. The Airtable was designed by UIC faculty member Dr. Howard Goldberg. It was then built by the shops in the UIC Physics Department. It is an important learning opportunity for our students and plays a major role in our physics laboratory instruction. The Airtable is used to record the position of a puck as a function of time. This means that you can trace the actual path taken by the puck and determine the time between points along that path. Before we go through the step-by-step procedure for setting up the Airtable, let's see how it works. The Airtable consists of a smooth glass surface in a wooden frame with adjustable legs. Flexible tubing connected to a compressed air system supplies air to a puck. This valve may be opened to use the secondary air hose if two pucks are to be used. The air flows through a copper sleeve in the center of the puck, so the puck floats on a cushion of air for low friction movement. A pointed needle, made of brass for durability, is soldered to the copper sleeve. A metal coupler on the air hose makes an electrical connection to a high-voltage power supply called a spark timer. The spark timer can be set to spark at 1/60th, 1/30th, or 1/15th of a second. Conducting carbon paper taped to the glass is clipped to the ground terminal of the spark timer. White butcher paper or a large graph sheet is placed over the carbon paper. Now, when the spark timer is turned on, a high-voltage spark will jump from the needle of the puck to the carbon paper, which is grounded, leaving a black dot on the underside of the white paper. The moving puck leaves a trace of black dots showing its actual path. Since the time interval between sparks is constant, the spacing between the dots indicates the velocity of the puck. So you see, the trace is a record of the puck's motion as a function of time. These two control boxes are used only for selected experiments. The first control box, called the roller speed controller, drives the front roller. The front roller is used for special functions, such as pulling paper across the table. The second control box, the motor cam speed controller, controls the motor cam drive on the side of the Airtable. The motor cam drive provides side-to-side motion or lateral force to the puck through springs. Accessories and additional features make the Airtable a versatile piece of apparatus that can be used to conduct many different experiments. It is important to practice the following safety precautions. Metal parts of the puck are at high voltage whenever the spark timer is turned on. Handle the puck only by its insulating ring when the power is on. Stay clear of the high voltage terminal and connections. Your body may provide a low current path to ground. Therefore, the current could jump and shock you if you are too close.
Ow! Oh, what happened?
I don't know. It shocked me.
Use only as much air pressure as is needed to float the puck. Too much air pressure can damage the hose and even cause it to explode. Do not look into the air hose or direct the airstream to any part of your body. Rust sometimes forms in the air supply. Particles of this rust may be blown out with the airstream and cause injury. Let's set up the air table for general purpose use. Place a piece of carbon paper on the glass, black side up. Tape the corners of the carbon paper. Use small pieces of tape to minimize tape interference with the puck. Make sure that the carbon paper is smooth with no holes so that the puck remains free to move and does not get stuck. Make sure that the spark timer ground lead is clipped to the carbon paper to complete the path. Most experiments require about 60 centimeters of white paper, which is the approximate size of the air table. Tear a length of white paper from the roll. Tape it to the glass over the carbon paper. Be careful not to tape it to the carbon paper itself so that the carbon paper is not damaged when you remove the white paper. Many experiments do not require the second air hose. Close the valve to the second air hose if it is not to be used so that the open line does not cause a drop in air pressure to the puck you are using. Place the steel puck on the air table. Loosen the needle adjustment screw until the needle is resting on the air table. Then tighten it. This will ensure that when the puck is floating on air, the needle will not drag and tear the paper. Connect the primary air hose. Slowly open the compressed air valve until the puck is floating. Use only as much pressure as is necessary to avoid causing damage to the hose. For most experiments, the table must be level so that the floating puck is not pulled off course by gravity. With the air supply on, adjust the legs of the air table until the puck is as stationary as possible on various spots on the table. Any drag caused by the air hose should affect the puck equally from all sides. Set the spark timer to 60 cycles per second. Make a practice launch with the spark timer off to get a feel for it. Make sure that each lab partner knows what to do and can do it without interfering with the other. To make a trace, turn on the spark timer and launch the puck, touching only the insulating ring to avoid getting shocked. Turn off the spark timer. Set the puck aside in a safe place so that it won't fall and cause injury to a person or damage to the equipment. Remove the white paper and turn it over to reveal the spark trace. This is a spark trace made by launching a puck by hand. Dots are close together when the puck is moving slowly. As the puck moves faster, it travels farther in 1/60th of a second, so the dots are farther apart. The puck's velocity v is equal to the distance it travels, delta x, in a period of time, delta t. If there appear to be missing dots or extra dots, check the spark needle. For instance, if the needle is too high, place the puck on the glass and loosen the adjustment screw until the needle falls to the glass. Then tighten the screw. If the needle is bent, ask the prep room attendant for a replacement. Now that the table is set up, we are ready to proceed with an experiment. In this section, Laboratory Experiments Using the Airtable, we first demonstrate the experiment Simple Harmonic Motion. Next, we will list some additional laboratory experiments and the Airtable accessories required to conduct them. In this experiment, Simple Harmonic Motion, we will use the Airtable to observe the motion of an object subjected to a force which is directly proportional to displacement. A simple linear spring provides such a force. As the spring is stretched, it exerts greater force. We will observe the one-dimensional motion of a puck subject to the force of linear springs. The experiment is divided into 3 parts. In part 1, a linear spring, we will obtain the force versus the stretch property of a linear spring. In part 2, simple harmonic motion, we will examine the simple harmonic motion of a mass moving under the influence of a linear spring force. In part 3, resonance, we will investigate the effect of adding to this force a particular type of time-dependent force. Part 1. Obtain the force versus the stretch property of a linear spring. For this experiment, we will need 4 springs, a meter stick, a mass set, and graph paper. Remove the 4 springs from the accessory board and ask your prep room attendant to replace any which are stretched out of shape. Place the loop of 1 spring on the screw on the front of the accessory board. Place a meter stick next to the spring so that the stretch of the spring can be measured. We will start with 20 grams. Wait for the spring to stop oscillating. Take the reading at the bottom of the spring loop, 51.8 centimeters. Record the reading for the first mass. We will repeat this procedure and record the meter stick reading for 50 grams, 100 grams, 150 grams, and 200 grams. Next, we will graph our data. We have converted the masses of the weights to forces by multiplying by g, the acceleration due to gravity, and we have graphed them in newtons versus the stretching of the position of the bottom of the spring in meters. We see that the plot is more or less linear. The slope of the line describes the spring constant. By taking the rise over the run and making sure that we have the correct units, we derive a spring constant expressed in newtons per meter. The spring constant is equal to the force required to stretch the spring a unit length. Simple harmonic motion of a mass moving by the force of a linear spring. For this experiment, we will need the Airtable, using the roller speed controller which drives the front roller, a steel puck, aluminum rods to restrict the puck's motion to 1 dimension, 4 springs, 4 socket cap screws, a balance to measure the mass of the puck, about 2 meters of white butcher paper, and masking tape. First, level the Airtable. Thread the white butcher paper under the front bumper of the Airtable and tape it to the front roller. Thread the remaining paper under the back bumper and around the back roller. Do not tape it to the back roller. Position the guide rails in the notches. Thread the 4 socket cap screws from the accessory board into the holes on the steel puck. Measure and record the mass of the puck. Place the puck between the guide rails so that the widely spaced screws face the sides of the airtable. Connect each of the 4 springs between a screw and the notches on the bracket at the side of the airtable. Connect the air hose. Turn on the air and allow the puck to come to rest. Turn on the spark timer briefly to mark the puck's equilibrium position. With the sparker off, displace the puck about 10 centimeters and release it. Observe the resulting motion. The time required for one complete cycle is called the period of motion. We will now make a spark trace, which will enable us to measure the natural frequency with this theoretical prediction, as explained in your lab manual. The oscillating frequency is equal to 1 over 2 pi times the square root of the spring constant divided by the mass of the puck. Locate the roller speed controller which drives the front roller. Set the puck to oscillating as before. Turn the controller on and adjust it so that the rollers pull the paper at a moderate speed. Turn off the spark timer and the paper drive. When the puck comes to rest, mark its equilibrium position with the sparker. Join the 2 equilibrium dots with a straight line. This line acts as a time axis for your trace. All points on it represent the equilibrium position of the puck. Mark the period of motion and measure the time of this period by counting the dots from one marker to the next. How does the measurement of the natural frequency compare to your theoretical prediction? Part 3, Resonance. Superimposing an additional time-dependent force on the mass. For this experiment, we will need the airtable, a steel puck, aluminum rods to restrict the puck's motion to one dimension, 4 springs, 4 socket cap screws, a meter stick, and a second controller, the motor cam speed controller, which is connected to the motor cam drive on the side of the airtable. Force is transferred to the puck through springs attached to this motor cam drive. The frequency of the force applied to this spring mass system is controlled with the motor speed cam controller. Adjust the motor cam speed controller so that the motor cam driving period is much greater than the spring's natural period, which was determined in Part 2. Estimate the approximate amplitude of the puck motion. Now, adjust the controller so that the motor cam driving period is much shorter than the spring's natural period. Again, estimate the approximate amplitude of the puck motion. Finally, try to adjust the motor speed so that the driving period is equal to the natural period of the spring. How does the puck move? How does the puck move qualitatively when the driving force has the same angular frequency as the spring mass system? What other observations can you make? Remember, accessories and additional features make the Airtable a versatile piece of apparatus. Additional experiments are kinematics of motion in one dimension, relationship of force, mass, and acceleration, projectile motion in two dimensions, impulse, conservation of momentum, the work-energy theorem in two dimensions, potential energy and force, and conservation of angular momentum. If you would like more information about the Airtable, please refer to your laboratory manual and see your laboratory supervisor.